There are multiple sizes of these surface mount components. There are a whole array. Basically it works like this. People want smaller because it's cheaper, it fits in your pocket, it has less parasitics involved, so it's easier to model. The smaller it is, the easier it is to model, but the harder it is to work with. So luckily they've come up with some standard sizes. So if I drew a resistor, and we do another resistor here, another resistor here, another resistor here. So these are all resistors, exactly the same. So this one, for example, might be what we could consider a 1210, and this one here might be 06, 03, 04, 02, and 02, 01. Now these are standard numbers, and what they actually mean is that you've got 12 mil in length and 10 mil in...
This is metric mil, not inches.
So this one's 6 mil, 3 mil, 4 mil, 2 mil, 2 mil and 1 mil, and yeah it does, and there is actually a 01, 0.15, which is ridiculous. And I've been in situations where I've been soldering 0201s under a microscope and thought, why isn't the solder working? And then realised I've actually picked up a piece of dirt and I'm trying to solder the dirt, not the real component. Yeah? It does happen, they are tiny. I'll bring some in next week, I don't think we've got some here. They are tiny, absolutely tiny, but if you open your mobile phone, that's what you're going to see inside, because it gets the overall size down. Yeah? Also, you are probably, in any job you take, never have the opportunity to design a product using through-hole. And there's multiple reasons for it. The first one's when you consider the amount of metal and materials needed to make one like this versus one like this, exponentially more. That's the first problem. The second problem is, if I have everything as surface mount, I can get a pick and place machine, put my board in, and the pick and place machine really quickly put them on the board, and then put the whole thing for an oven and reflow. Everything's soldered. I can't do that with these. Well, if I do that with a through hole, I need either a very special piece of equipment called a wave soldering machine that has a massive chamber full of molten solder, and your boards go on a conveyor belt across it, and there's a big wave machine in the solder, and it pushes the solder up onto the board and let go. And it solders most through hole components. It's very expensive, takes a lot of solder, takes ages to heat up, very dangerous. The only other option is to have a huge line of lovely people, each with their own soldering iron, as a massive production line. So you can imagine how much that's going to cost when I can automate the whole process using some of this. Yeah? So this is really where we're going to be. Through-hole is great for prototyping if you want to throw something together. Very, very surprised if you ever have the ability to work with that in your real life. Yeah? Because it's just not cost effective. So I've spoken about these standard resistors here, and I've got some here that I will send around so you can see. These are 0603. So what I'll do is I'll pull a few out. Where are these? Okay. So we'll send them around. Try not to drop them. So this is 0603. So we're here, okay? Normally now I work down here, you know, and occasionally I've got to go down here. So to work on 0603 is a bit of a luxury, to be honest. So that's our standard for resistors. Inductors use the same packages. Diodes mostly use this package. The only difference would be tantalum capacitors.
They are diodes that you got there.
And tantalum capacitors, they look the same, they're just much bigger. So here is our pad, there's a piece of metal that goes down like this, a piece of metal that goes down like this. We solder here, we solder here. And these are based on a case number. So you'll have case A, case B, case C, case D, and each one represents a set physical size. So depending on the size of capacitance you need in your capacitor, you look at the data sheet from the manufacturer, and they will say, yes, we can give you a 100 microfarad 16 volt tantalum capacitor in case C. So then you'll go to your software and you'll find the standard case C footprint and you'll assign that to your board. Yeah? So every single surface mount and through-hole component you choose to go on your board, it's up to you to look on the website to find which one you're going to buy, what footprint you need for it, and whether actually the component that you've chosen is available. Because there's no point in just grabbing a component, and I've seen this happen many times, and think, yeah, that fits perfectly, got the footprint, bam, 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 make 1,000 of them, and then you've got a year wait for that component to come in any kind of quantity. So you've got to think about all of those things when you're designing your board, yeah? What components am I using, what size I'm going to use, the price of it, and the availability of it. Yeah? All of that kicks in. Now the last thing I want to just touch on, we have some what looks like SO18s here. These are surface mount ICs, which I'll send around. And again, they come in a standard package. So let's assume it's an SO8. An SO8 would look like this. It's got 4 pins here, 4 pins here, and there will be a pitch, yeah? There will be a case size and a case length like this. An SO8 represents a standard 8-pin surface mount 0.5mm pitch IC. Now you might get a 0.4mm version, which I believe is a TO8, and you might get even less. You might get microchips like a QNPP or something like that, which has got pins on all sides. You might get a huge one of those with 100 pins, and those pins might be 0.3mm apart, so get much harder to solder. You might get a QFN part. A QFN part, if I take a side view of a QFN part, it's got little copper legs that go up the side, but they don't come out. So you're butting your solder joint. If this was your PCB here, and there was one here, you're butting your solder joint up against it. And then you've got BGAs, which are ball grid arrays. That is a part with lots and lots of balls on the inside that you never see. Obviously you can't solder it, but you can reflow it in an oven. So you put the footprint down, you put some flux on there, you put some liquid solder paste on there, and then you place the BGA part on there, put it in an oven, and reflow it. And that typically is how we would solder most of our surface mount components, and it's really quite an interesting effect because you don't even need to accurately place your components. Because what will happen, when it starts to reflow, the solder will melt, and then it will create a surface tension on top of that solder, and it will pull your device into exactly the right position. Yeah? And that's all down to the reflowing. So I think that's covered most footprints. Any questions? Any questions on PCB design? So it's all down to the capabilities. One last thing I will touch on PCBs quickly is the capabilities of the fab plant that you choose to manufacture your PCB. You're going to have a PCB, and then on that PCB you're going to have all kinds of traces. You might go over there, little bits of copper with holes in. Yeah? Now, your fab plant that you choose is going to have a limit as to what they're capable of producing. Yeah? And one of those limits is going to be the thickness of your track, your minimum thickness. The other limit is going to be the clearance between two tracks, the minimum clearance. And typically that's classed as a 6-6, which means you've got 6 thou minimum track width with a 6 thou clearance between tracks. Yeah? If you want to go to a 5-5 or a 4-4 or something like that, they can do it, but your cost will go up massively. This is specialised. When they etch this, they draw it on the board, and then they use some kind of ferric chloride or some kind of acid on there. So the actual trace does not look like this when it's finished. It looks more like this. Yeah? It's not an exact science. That's why those minimum widths are important. And the last thing is the minimum hole width, which might be 0.2 mil, 0.3 mil. If you go below that, they'll start charging you a lot more. So if you're going to make your own board and you want to send it off, do not go under. If you ask me, try to keep it at 10-10, which means 10 thou width, 10 thou clearance, and no more than 0.35 mil minimum hole. And then you'll get a prototype board that will cost you $1 if it's within 100 mil by 100 mil. Really cheap. If you go over those limits, your price will go up real quick. Okay?
Okay, so you can see why footprints are so important and why in multi-sim you've got that annoying step of defining what the footprint is. Because as you can see, it's an incredibly complicated thing to actually answer what component it is that you're using. Thank you, Mike.